Dylan Small, Nate Williams. Of course, this is all possible because of Renad, as well as our entire Penn team and our site PIs and the entire teams at Henry Ford Health System in Kaiser Permanente, Colorado, where we are implementing this study. To give you some background and motivation for the ASPIRE trial, as many of you know, the rates of adolescent suicide and accidental gun deaths are increasing. And of course, the risk of death is greater in homes that have an unlocked and loaded firearm. The Safe Firearm program is an effective program. It has been shown to increase safe storage, but it's not yet routine clinical practice in pediatric practices. The Safe Firearm program offers brief counseling about safe firearm storage and offers families free cable locks within child well visits. So for those of you that haven't seen a cable lock, which I hadn't at the start of working on the ASPIRE trial, it looks something like this and prevents the gun from being loaded. So the goal of the ASPIRE trial is to compare two different strategies to implement safe firearm. And those strategies include an EHR smart list that we have embedded within the EHRs at both health systems that we're implementing this study at. And the way that we've done this is we've taken the safety smart list and we've added these 4 items. So we've added, did you discuss safe firearm storage? Did you not discuss it? Did you offer a cable lock? And did you not offer a cable lock? So this will remind clinicians during the well child visit to discuss these things, to offer the cable locks, and then the clinician will click through whether or not they addressed each of these items. So that is one arm of this trial. The other one is to embed this smart list nudge and add facilitation. So facilitation is going to provide additional support to the clinics and the clinicians to enable them to tackle any sort of barriers to discussing and handing out these cable locks. Our design of this trial is a cluster randomized trial that is implemented within these 2 health systems. And one of the challenges is that we only have 30 clinics to randomize. So that's our unit of randomization is the clinic. So our primary goal is to compare nudge to nudge plus with respect to our primary and secondary outcomes. So we have made reach our primary outcome, and I'll discuss a little bit more about that later. And then our secondary outcomes include implementation outcomes such as fidelity, acceptability, number of cable locks distributed, and the cost of these implementation strategies. So some challenges that I want to focus on today are under the umbrella of challenges in cluster randomized trials when you have a small number of clusters. So there are many different challenges, but I want to focus on primarily these 3 things. So when you have a small number of clusters in a cluster randomized trial, you introduce the danger of having bias due to confounding. There's issues with respect to low power, and then it can be very difficult to correctly specify the correlation structure of the data, because when we're working with clusters, and specifically with ASPIRE, we have patient visits that are nested within practicing clinicians that are nested within these clinics. And there are some additional complexities of the correlation structure. So the problem is that if we misspecify this correlation structure of the data, that can additionally lead to bias and possibly lower power. So the first challenge that I want to focus on is this potential for confounding bias. So first of all, what is confounding? If we have some set of treatments that we're interested in comparing with respect to some clinical or other outcome, then a confounder is something that potentially influences the assignment to those various treatments, as well as has an effect on the outcomes of interest. And a classic example of this is if certain patients are sicker, and so they tend to get the experimental treatment more often than other patients. And then also, if those sicker patients tend to have worse clinical outcomes, that can result in the sickness of the patient being a confounder of the treatment effect. And it can make it look like this new investigative treatment is potentially harmful because those sicker patients tend to have worse outcomes. So if you don't account for that confounding in the analysis, it can lead to bias in the estimation of those treatment effects. We can address confounding in several ways, and I'll talk about how in the Aspire trial we've tried to address potential confounding at the design stage using a particular type of randomization. And then another way to address confounding is at the analysis stage by adjusting for potential confounders if you've measured them. The challenge with a small number of units of randomization is that randomization only works as the number of units to be randomized grows, is large enough. So if we can achieve this balance across treatment arms on both measured and unmeasured confounders if we have enough units to randomize. And so in small samples, we can, by chance, end up with some clusters or some clinics that have a certain value or distribution of the confounder just by chance, and we can end up with this imbalance across the treatment arms. So some design approaches to potentially achieve balance in small samples to make it more likely that we achieve balance across the treatment arms are things like stratification. So if we have a number of variables where we know that they can potentially influence the outcome, and so they're important prognostic variables that we want to balance across the treatment arms, we can stratify on those variables and make sure that we're balancing the allocations within those strata. Another idea along this line is a match design. For example, maybe a matched pair design where you take two clinics that look very similar on a lot of these important prognostic variables, and you randomly assign one of them to intervention arm A and the other to intervention arm B. What we decided to use for Aspire is a type of randomization called covariate constrained randomization, or CCR. And the advantage of CCR is that it ensures that we achieve similar baseline covariate distributions across arms on based on a number of variables that we believe are prognostic. So they have an effect on the outcome. And with a small number of clusters, it's really important to be judicious about choosing covariates for CCR, because in order to account for the design stage, we need to add these variables into our analytic model to be able to address and control the type 1 error, as well as increase power. So these variables that we're trying to balance using CCR, because we believe they're prognostic, it's going to help us increase power if we additionally adjust for them in our analytic model. But because we have a small number of clusters, we don't want to, or we aren't able to just throw all of the variables in there. We can't just include everything with the kitchen sink in our model because we have such a small number of degrees of freedom. And so we have to be really judicious about what we choose. So we spent a lot of time discussing with our site PIs and the entire team what they thought would be most influential on these implementation outcomes of interest. And we ended up deciding to completely stratify by health system and then use CCR to balance both clinic size as measured by the number of well-child visits in the last year, as well as the presence of a clinician stakeholder. So some of these clinics that we're randomizing, we have clinicians who practice there who are a part of the Aspire team and are influencing the decisions that we make. And so they're likely to advocate for this program and potentially increase the rates of reach and fidelity at those clinics. So we wanted to make sure that we balanced on whether or not there was a clinician stakeholder at these clinics. The second challenge that I want to discuss is how to choose the analysis model. We've spent a lot of time deciding on this amongst the statistical team and as well as the broader Aspire team. So mixed models are useful for hierarchical data. We can possibly include random effects for clinician as well as clinic. But some drawbacks of using mixed models are that they require correct specification of the mean and the covariance structure. And we have a potentially very complex covariance structure in the Aspire trial that might be difficult to specify. And the other disadvantage of mixed models is that the interpretation of the effects is conditional on those random effects. And in Aspire, we're really interested in, well, what if we were to give all of the clinics just the nudge versus what if we were to allocate all of the clinics to nudge plus? What would be the difference in outcomes if we had two hypothetical potential world where we could assign all of them to one treatment and then another world where we assign all to the other treatment? And so that's a marginal effect that we're really interested in. And the nice thing about the model that we decided on was that it naturally gives us this marginal interpretation of the effects that a mixed model does not. So some other considerations in the Aspire study is that our outcome is binary, both reach and fidelity, which are two very much of interest to us as outcomes. And this idea of having to correctly specify the covariance structure was, as a statistician, making me very nervous because as we learned more about these clinics, we learned that some of the clinicians work at multiple clinics. We also know that family members, we can see multiple children from the same family at a particular clinic or maybe at multiple clinics within a network. And so the idea of correctly specifying the correlation structure, given that some of these clinicians might work at multiple clinics, seemed very daunting to me. And so I and the statistical team, we ended up choosing to use generalized estimating equations because of the advantages that they provide, such as being robust to misspecification of the working correlation structure, as well as naturally providing marginal interpretation of the effects. So this robustness, though, in order to have this robustness property of the GEE, it depends on having a large enough sample size or a large enough number of clusters. And so given that we only have 30 clinics to randomize, we looked into this issue, and there's been a lot of work in the statistical literature on small cluster corrections. So when you don't have a large enough number of clinics, then GEEs tend to underestimate standard errors. So this can lead to more liberal inference, meaning that the p-values can be too small, we can make too many type 1 errors, and our confidence intervals can be too narrow. And so again, we would be making too many type 1 errors with that liberal estimation of these standard errors. So what these small cluster corrections do is they tend to inflate those standard errors to adjust for the fact that we have a small number of clinics, but then retain this property of being robust to misspecification of the working correlation structure. So finally, some other considerations that we are still thinking about and still discussing amongst the team. Our primary hypothesis, we kind of went back and forth as to whether we wanted to study whether Nudge Plus was superior. So is it more effective than Nudge, or are these equivalent, which would be a nice conclusion given that Nudge Plus requires more resources and is more costly. And so if given some margin, we could say that Nudge and Nudge Plus are approximately equivalent with respect to effectiveness. Maybe we could recommend scaling up using only the Nudge, which is less resource intensive and less costly. So we've been proposing to use a novel statistical hypothesis testing framework that would allow us to test both of these hypotheses. So specifying several different null hypotheses without having to adjust our type 1 error. So it sort of allows us to study both of these questions without penalty with respect to our alpha level. Another consideration is that we ran a pilot study implementing the nudge at a few different clinics. And unfortunately, the parent survey response rate for our fidelity outcome was quite low. So it was about 20%. And we were able to increase this pretty much double the response rate by using a very resource intensive approach. And so we were able to get that up to about 40%. But even at that 40%, using all these additional resources, we were a little bit concerned about the generalizability of the results given this response rate for the fidelity outcome. And this led us to actually switch our primary outcome from fidelity, which is what we specified originally, to reach, which we have a little bit more confidence in, given that it's collected from the EHR. However, reach sometimes can over or underestimate the true delivery of the program, which is what we're really interested in. So we're now sort of in discussions about having using statistical methods, novel statistical methods, to be able to use a small gold standard sample of fidelity that we would sort of go all out for. We would put all of our resources into getting a small parent sample to get a good handle on what fidelity truly is, and being able to use that gold standard sample to adjust for potential bias in the reach outcome, which may result from clinicians maybe clicking through very quickly, making errors, or exiting out of the SMART list, and potentially having that to default to a yes or a no answer, leading to bias or measurement error in that reach outcome. So there's a lot of work in the statistical literature on this to correct diagnosis codes in claims data, in analyses that use claims data that rely on diagnoses if we're trying to study risk factors or comorbidities for certain conditions. Claims diagnoses are notoriously prone to error. And so there's been a lot of work in the statistical literature to combine these intensive gold standard samples with the measurement error prone variable to decrease bias in the analytical model. So with that, I'm going to hand it off to Alisa. Alisa, do you want to use your own continuation of these slides? Oh yeah, I think you're still on mute.
Thanks. I'll use my own.
Okay.
So, okay. Can everyone see?
Looks good and we hear you.
Okay, perfect. So I actually will touch on some of the same issues that Kristin talked about. And I'll first detail the implementation science trial that I've been working on, which is handoffs and transitions in critical care, understanding scalability. And our PI is the wonderful Megan Lanefall, who's on this call. And so the objective of Hat-Trick is to look at the effect of implementing a tailored handoff protocol among clinicians in the OR and ICU in order to prove fidelity handoff elements and improve clinical outcomes. So the design of Hat-Trick US is that it's a stepped wedge type 2 hybrid effectiveness implementation trial that consists of 12 ICUs. And so as this stepped wedge design goes, it's a sequential one-way crossover design. So in sequential periods of 6 to 8 weeks, sites will cross over from starting in the control state to then crossing over into the intervention state. Will they be implementing this tailored handoff protocol? As part of this design, one of the issues that we were concerned about is contamination within hospitals, because some of our ICUs are within the same hospital. And so we were concerned with if we randomize 2 ICUs within the same hospital at very different times, that there could be contamination of the stage because one ICU that gets schedules crossover later might hear that the other ICU in the same hospital is implementing this new thing. So one of the constraints that we used in our randomization was to randomize the hospitals and then randomize within hospital the exact start time. The co-primary outcomes of Hattrick US are fidelity and effectiveness, where in our case, fidelity is this count of the number of handoff elements that are satisfied by the clinicians involved in the handoff. And so they include things like introductions of clinicians, surgery and anesthesia reports, and huddles in order to maximize information transfer regarding the patient that's being handed off from surgeries to the ICU. And then the second is effect for our effectiveness outcome is number of new onset organ failures, which is an ICU level outcome. So the step wedge design is, I feel, all the rage, but it does have some caveats that investigators who implement it need to be aware of. And the one of the major ones is this built-in confounding by time, because time is inherently associated with when clusters switch over into the intervention state. And so as time goes on, the likelihood of being in the intervention state increases. And so stepped wedge cluster randomized trials are more sensitive to secular trends. And so in addition to the kind of small sample confounding, which is somewhat mitigated by the stepped wedge design because we do use within cluster information in order to estimate treatment effects, but we do now have this confounding by time. And so in detailing our analysis plan for Hattrick US, we wanted to be careful about things that could vary over time and associate with outcomes, and make sure that we stated up front that we would consider adjusting for them in some way. And so for our implementation outcome, we thought that it would be relevant to adjust for the ICU type. So we had pediatric ICUs, cardiac ICUs, or other types of ICUs. Indicator of a PACU stop prior to going to the ICU, which is a difference in flow across hospitals with regard to how patients transition into the ICU, ICU volume, whether it was a readmission, and the number of surgical services. And this we thought was a proxy for familiarity and familiarity with working together among clinicians. And then for our effectiveness outcome, we also considered ICU type, ICU volume, and number of surgical services as potential confounding variables that we wanted to adjust for in our analyses. So model misspecification is also a really important or critical feature of the analysis of a stepped wedge cluster randomized trial. So it's common to use mixed effects models where the fixed effects are include intervention and the time period, and then there are random effects for sites. And then there could be, there should be site as a random effect, and then we have site's heterogeneity for the intervention and time that we could also enter as additional random slopes. And so for our implementation outcome of fidelity, we consider a mixed effects model where we have a random intercept for sites, and we have a time fixed effect and the intervention effect as this theta. And then for effectiveness, we want to account for potential differences in ICU volume because we're using an ICU level outcome. And so our outcome, which is number of new onset organ failures, we want to account for differences in the number of patients being admitted to the ICU. So we have that as an offset. But there's been literature recently that suggests that omission of site treatment or site time heterogeneity can lead to biased intervention effect estimates and also standard error estimates. And this is along the same lines of what Kristin just spoke about with misspecifying the correlation structure. And so it's recommended, if possible, to fit this larger model that has these random slopes slopes for the intervention and time effects. And so we've written that into the analysis plan for hat trick in order to see if this changes our inference and conclusions at all. However, it is a challenge to fit these models that have these additional random effects because the model convergence is not guaranteed as the model becomes more complex. And so it's not a guarantee that you can actually fit this model, in which case it's recommended to conduct sensitivity analyses to again see what the impact of this site heterogeneity is and on treatment effects, on estimated treatment effects. So we do have semi-parametric alternatives, as Kristin just mentioned, which is the GEE. As she also mentioned before, we do have to worry about small sample corrections to the variance estimator if we have fewer than 40 or 50 clusters. So we haven't chosen to go down this route for hat trick, but it's an important methodological consideration for the analysis of step-wedge randomized trials. Here, it has been investigated that you can use these small sample corrections. I think I initially was concerned that the number of clusters was so small in step wedge designs that I wasn't sure that the small sample corrections would help enough. But there are some recent papers that show if you have 12 clusters or more, that some of the corrections do recover the right type 1 error and coverage. There's also some randomization inference that's been done for step wedge cluster randomized trials. So that's another alternative form of inference that can be done if concerns about the variance estimates from more asymptotic based techniques, such as these estimation method techniques, are not, if you're not confident in those. And then some recent and ongoing innovations. We've had some really interesting discussions within our hat trick team about characterizing fidelity over time and recognizing heterogeneity in the sites with regard to, well, what does it mean to be to have fidelity at that site, and what are the handoff elements that we want to prioritize at given sites. And so we discussed that it's possible that we may want to consider a changing definition of fidelity over time based on an individual site's needs, and that fidelity might not be the same from site to site because different sites have different needs with regard to what they need to target for their handoffs. And so although this hasn't been done in the past, that we would kind of change fidelity across sites, we spoke about how we can operationalize that using offset terms and different features of model specification to accommodate that. We've also had some interesting discussions about conceptualizing implementation as a continuum rather than a binary variable. And so we can think about there being multiple stages of implementation and potentially characterizing our intervention ordinally and thinking about different stages and potentially estimating the effects of reaching each stage. More along the lines of thinking of lagged effects over time or changing effects over time, there is some recent work about an effect curve for implementation. So maybe the effect of the, not the exposure itself or the intervention itself, but maybe the effect of it varies in time. So rather than estimating a single parameter, we can estimate a function that displays the effect of the intervention over time. And so all of this made me think a little bit more about instrumental variable methods, because we only have a single randomization of start times for each of the clusters that are involved in a step wedge design. And so when we think about them reaching different stages along a potential implementation continuum, then we're no longer randomized, right, as far as when they reach that stage. And so that's a common scenario in which we appeal to instrumental variable methods. But within this context, we do have to think about the plausibility of assumptions such as exclusion, know and measure confounding of the instrument, and things of that nature. So I think these are more things to think about within the analysis of stepped wedge cluster randomized trials. And then here are a bunch of references in order to investigate these topics more closely. And with that, I will close and we can, I guess, enter the question and answer phase.
Yeah, that was great. Thank you both so much for sharing your research with us. As Renat's giving a round of applause. I'm sure that sparked a lot of questions, but perhaps we can start with a few broader questions, given that we have a mixed audience for folks who may not be as familiar with the technical terms in biostatistics. And of course, as you all come up with questions, please put them in the chat. But perhaps we can start. You both described different studies, and was hoping you could tell us a little bit more about how we select the appropriate study design. And of course, the research question will inform our study design, but are there particular designs that you recommend for implementation science studies? And then conversely, are there any designs that you recommend avoiding?
I guess I'll start. I think that the cluster randomized trials seem to be very relevant because of the nature of the interventions, tending to be things that involve a lot of staff or a higher level organizational unit. And then within cluster randomized trials, there's this question of whether you do a parallel, whether you do a stepped wedge. And so the stepped wedge design, it allows you to use fewer clusters because you're relying more so on the longitudinal nature of it. But it does have all of these additional assumptions that are layered in because of the secular trend issue. And so there are some trade-offs to be considered in deciding between those two.
Yeah, I agree with that. I've also recently been working on some trials in other areas that have sort of combined cluster randomization with individual randomization. So if you had some study question that, or if you had some implementation strategies that could be implemented both at the clinic level and potentially nudging people at the individual level, thinking about novel ways to combine two different types of randomization. And then I'll also follow that up with saying that one of my areas of expertise are sequentially randomized trials. And so I would be really interested in pursuing questions in implementation science where if there's a sequencing aspect to it, like if you maybe come out with the first strategy to implement something, and if there's some way to measure a non-response to that, and then follow up with additional nudges or additional implementation strategies. I think a smart design, sequential multiple assignment randomized trial could be an interesting future direction for some of the questions in implementation science.
Yeah, that makes a lot of sense. And there's actually a follow-up question that we received before the event today, but Kristin, you touched on it in your description of Aspire, but can you expand on the difference between a covariate constrained randomization versus stratified or max randomization method in clustered randomized trials?
Yeah, I've learned a lot about this recently, so I don't claim to know everything, but in what I've learned, the covariate constrained randomization balances functions of multiple variables, so it can potentially be useful when you're unable to stratify on multiple covariates that you think are potential confounders and prognostic. With stratification, when you do have a small number of clusters to randomize, you can get into a situation where you have very small strata, and then you can end up with imbalance because you don't have enough clinics to randomize within some of those small strata. And what covariate constrained randomization does is it enumerates all possible allocations of, say, the two arms or the two interventions to the available clinics. And it computes a metric of balance that is a combination of balance on all of those covariates that you're trying to make similar across the groups. And then it restricts the randomization to a portion of those allocations that achieves what you deem as good enough balance on that combination of covariates and the distribution of that combination. and then randomly chooses from that subset that does achieve good balance. So I think that it's kind of, it trades off trying to achieve balance in a larger sense versus trying to achieve very fine-grained balance on a number of covariates that a stratification would do.
That was really helpful, thanks. And you actually sparked another question, just generally about power in general. You mentioned the small sample size, which I feel like is something that we're considering when looking at traditional study design. But thinking about implementation studies, how can we ensure that we're appropriately powered for statistical analyses given the limited information we often have on implementation outcomes?
This is a really challenging question. I'm going to defer to Alisa since I see that you've unmuted yourself.
Oh, it is a really challenging one. And I think that's more so of a plug to investigators to release your data, like release your estimates of correlation and your intracluster correlation coefficients and correlation measures over time, because I think that's where we always run into challenges. It's well, what do I assume about this correlation? And if my correlation is this, then our power is this. And if it's not, so I think in the absence of that information, we try to come up with a reasonable range of things to assume, and then show that we're reasonably powered under like a worst case scenario type of situation. But oftentimes that requires us to be a lot more conservative than we need to be. And so as much as people can, when you're reporting your studies, publish those correlation coefficients, because it's really helpful for the next person.
Yeah, totally. I've done some simulation studies, and I think that simulations can be useful, but they still require a lot of assumptions. And so I agree with Alisa that if you can, definitely those ICCs, I mean, that really has such an effect on the power, and we really have such limited information. And even the idea of ICC in something like Aspire, where it's not exactly clean that clinicians practice within the same clinic. You have this spillover. I think that's really, it gets really complicated, and yeah, simulations can give you some intuition, but they have limitations as well.
I see a follow-up question about, does that go into the regular tables or in a supplement to the main outcomes paper? If you can fit it in the results, I think that it's a fair place to put it. People don't go to supplements that often. They have to be really looking for it. So yeah, I would recommend putting it in the results of the main paper if you can.
Great. We actually have another question in the chat from Kate. Can you speak to how and when one might use a cross-classified model to deal with non-hierarchical settings like many healthcare systems?
I'm not actually familiar with what this term is. What is a cross-classified model?
I've seen it in, it's been used in observational studies when you're dealing with like neighborhoods that people don't, of course, nest nicely into neighborhoods. And there's been some discussion of using it in healthcare settings, which is exactly you raised, right? Patients don't nest nicely in providers and clinics and hospitals. We like to pretend they do, but so that's, it's a model that I know about this much about. So, but it is a non-hierarchical model. So I just don't know if it's been used in trial settings to evaluate it when you have that messiness going on, or reality. And if you don't know, that's fine.
Well, you know this much more than I know about.
I have definitely, I can't name a trial that has used cross random effects, but I have definitely seen the models specified before, and it wouldn't surprise me if it has. And I think there's a good argument too. So I think that is one of those things that can and maybe should be done. And it would require, getting out that mixed effects modeling textbook for looking at the exact model specification and implementing it with regard to, your exact scenario. But I think that's a very useful suggestion.
We need a biostatistics PhD. to do some work here.
Yes, yeah, that's where we come in. But yeah, we all we've seen these things in classes. A lot of us have. But I have not implemented cross-random effects.
Okay, awesome. Thank you.
To expand on that, Kate, thanks for giving us a new approach that we can learn. We'd love to hear what opportunities you see for cutting edge methods in implementation science.
Oh.
Alisa, you're unmuted. Do you want to go first?
I forgot to mute from answering the previous question. I think it was just some of the things that I talked about, which I think have to some extent been done already, but I think that, you know, new cases warrant new circumstances and could potentially involve additional tweaking. And so I am interested in delving more into the IV literature for separate edge trials. Randomization inference is interesting because it's, you know, robust to all of these model assumptions that we need to make, and just relies on the randomized sequence. And so I think that's a really powerful tool with regard to valid, robust inference. And I have not seen randomization inference used or discussed really. I mean, it was something I looked up and saw that there was one reference for it when I was preparing. But I think that it is potentially more that can be done there. Yeah, I think I'll stop there.
Yeah, in addition to some of the things that I mentioned about maybe combining multiple outcomes and using the strengths of each one of them to get a better understanding of the true fidelity of these implementation strategies. Another area that I'm really excited about and interested in as far as statistical methodology is personalization of treatments, individualization. And I don't know that we would have the power and the sample size in Aspire to do this, but I could imagine that some clinics, some types of clinics might benefit more from Nudge Plus, whereas other types of clinics, the nudge might be great and be sufficient to really increase adoption of these practices. And so if we could learn about what types of clinics to spend our resources on, I would be really interested in pursuing those methodological challenges and applying them, applying methods to be able to figure that out. But yeah, I think it's going to be tough.
Yeah, that makes a lot of sense. And something that I'm particularly excited about is the mechanism work in implementation science. And I'd love to hear your thoughts on how we can assess causality specifically in evaluating mechanisms between implementation strategies and outcomes.
Yeah, so I think this is a great point. And causality, you know, as I'm trained to think about it, is always about teasing out common causes. Because if you have a common cause of something, which we call a confounder, right, then that makes it hard to see if we have that causal relationship between two variables. And so to the extent that you can collect information about common causes of things, you would need to collect that. And thinking about the appropriate intermediate variables to collect as well, that would allow you to tease out some of those pathways.
Thanks. I'm also really interested in that given my epi background, so I appreciate that description. We had another question come in from our Pisces community, and I feel like it's one that probably many folks are thinking about. So is it better to develop new measures for an implementation science concept that is not piloted, or to use a validated measure that doesn't measure the concept well?
It's a great question. I don't have a great answer, but in thinking about the response rate to the survey that we've experienced in the pilot for Aspire, I wonder if there additionally are other considerations that could help answer that in some situations, where if it's possible that the newly developed thing that hopefully measures what you're trying to get at a little bit better, but is not validated, Maybe if it also leads to a higher response rate, that would be a consideration as to what to use. But I do think that thinking about publication and convincing reviewers, is probably easier to convince reviewers of something that has been validated.
Yeah, I would say in that scenario, it sounds like it would be beneficial to do a validation study first. If you're concerned about a measure not being the best for your problem, then you've noted that there's a gap in the literature and a gap in methodology. So I would suggest actually writing a preliminary paper that validates what you plan to use and justifies why it's better than what's out there. And then once you do that, you can feel more confident in using it in your subsequent study. This is assuming that you have the time to do that.
That makes a lot of sense. Another question that came in was something that I also think is on many people's minds, given the approach to do hybrid effectiveness implementation trials. For those who are not familiar, that's where we're evaluating both the clinical outcomes and the implementation outcomes in the study. So what are the statistical limitations in pursuing such a design that we should be considering?
So this is a new thing for me as I become more involved with implementation science. But anytime there's co-primary outcomes, I'm always wondering, what is done with type 1 error control? And so I don't see that it's been something that has been addressed in the literature and typically concerning. I mean, there are different ways that people think about multiple comparisons, and there are ways that you can kind of justify like not accounting for it if you can kind of conceptualize them as separate studies. And so it's something that I think about, but I'm not sure that I have the best answer for yet. But that's always where my mind goes first when I hear about there being multiple outcomes is type 1 error control.
That's helpful, thanks. And thinking of errors and bias, another question that we had received previously is thinking about how in implementation science we target specific stakeholders, and that's really key to the implementation work. How can we mitigate potential selection bias that may influence our results?
It's a great question. I think it's really tough, but if we can measure a lot of things to try to be able to characterize it, then there are ways that we can adjust for selection bias in the analytic model. But there's always this question of, have you captured that sufficiently? If we're going to try to address this at the analysis stage. And so I'm a little bit less familiar with sampling and novel methods in sampling, but there might be ways to address it at the design stage that can help, improve and reduce bias at the analysis stage.
I think that with these selectivity questions, you have to identify who your target is and the data that you're actually getting and what the difference is between the two. And if you've measured those differences, then we can appeal to our epi knowledge again for doing things like weighting and calibration and things of that nature. But I would say those are the kind of key elements. What is the discrepancy between who we'd like to perform inference on and who we're actually getting based on relationships with stakeholders? And have we measured the way those things are different? And if so, then we can do something about it at the analysis phase.
Thanks. Yeah, these are hard questions, so apologies for that. But great responses and really helpful. We've been scribbling down a lot of notes. Maybe as our last question, would love to hear your parting thoughts on what our key takeaways should be as we're thinking about designing our implementation science studies.
I've really benefited from having a full statistical team. So I know it's quite an investment, but to just have multiple people with various expertise, even within statistics, to bounce ideas off of has been really beneficial. And so I think when planning for grants, allocating enough effort for at least one, but better if more than one, if possible, statisticians on the team.
Agreed. And also, we always say this, but consult us early. I think there's a thought that the statistics doesn't come in until the end, right? And so, where it's best when we're involved in every aspect of the design. One of the issues that came up on hat trick was assessing multiple people or assessing people repeatedly over time. And it wasn't discussed how these people would be tracked. And so we decided, or we realized that, we need to come up with some identifier to track these people. Otherwise, we won't be able to do any statistical inference. And so just consulting statisticians early and frequently. And yeah, again, having a team is really helpful. And know why you're choosing your design, I guess, is another thing too. Just make sure that you're justified in using it. And I think that's the biggest controversy right now, if there is one, with the use of the stepped wedge is make sure it's justified. So I think those are some things I would mention.
And I think those are great points to end on. Before handing it over to Renau, I just want to thank you both so much for sharing your expertise. I'm sure we all learned so much from you. So thanks for being here. And Renau, do you want to close us out?
Yeah, I want to thank our colleagues for their brilliance and generosity with their time and insights. This is an area that is really emerging, and I know I've learned so much from these colleagues, and will continue to look to them to be at the cutting edge and lead the field at the intersection of biostatistics, methods, and implementation science. So thank you so much to everyone.
Thank you for having us. This was fun.
Yeah, thank you so much.